I'd like to talk about the cool new technology called fully homomorphic encryption or FHE, and in particular a library from Google in C++. This library promises that developers and not cryptographers and mathematicians can use it for FHE programs, and since I'm just a developer, I decided to give it a try. First, I'll start by saying a few words about FHE, give a very brief overview without any technical details, and then move on to implement a simple example for mailspam detection in this library, run it and see how it works. So let's start with the FHE overview. So let's suppose we have a client server architecture. We have a client here and we have a server over there. And let's suppose that this server is exposing a function that sums two integers. So it gets a pair of integers from the client, a and b, and computes their sum and returns it to the client. This is obviously not an extremely useful server, but it's good for examples. In a traditional client server architecture, what's interesting is that for the server to be able to compute the sum of a and b, it needs to know what the values are of a and b. And even if the communication between the client and server is secure, like for example it could be TLS or could be over a VPN connection or whatever it is, the server needs to know the values of a and b. So what will happen typically is that the client will encrypt its whole message, and the server will be able to decrypt it, get a and b, and compute the sum. And obviously, if there's some person in the middle looking at their communication, he or she will not be able to guess what a and b or the sum is, but the server will know it. And what FHE allows us to do is to make sure that the server can compute the sum of a and b without knowing a and b. And just to give a brief detour and explain what the real application might look like is, if you think about how Google Maps works currently, is that it gets your current location and possibly, let's say, a destination you want to go to, and on the server side, on the cloud, it computes the route and returns it to you. But maybe you don't want to share your location or where you're going, and this technology can allow you to hide this information from the server. So let's get back to our simple example here. What the client might do instead of sending a and b, first of all, it can encrypt a and b, so it can do encrypt a and also encrypt b, and send these encrypted versions to the server instead, and it will do so with its own private key. This key will not be shared with the server. And what's fascinating about FHE is that the server can, even though it doesn't see a and b, it can still compute their sum and return something like an encrypted version of a plus b without seeing a and b. And what's really cool is that only the client with its private key can decrypt the answer. So the server doesn't see a and b, it doesn't even see the sum that it computes. And this is, I hope, really powerful for the future. It can give us lots of interesting applications, provided that it's fast enough and it's usable. Let's move on to the library itself. As I mentioned, it's being open sourced by Google recently. This is the URL and I'll share it in the description. On a very high level, what this library does is it gets your C++ program and it transposes it to a special type of a C++ program that can work on encrypted input. And this happens in the transpiler directory, so let's dive into this directory. What they say in the beginning is that they connect two libraries together, the XLS library and the TFHE library. I'm not a hardware expert, but from what I've seen, XLS is a library for hardware synthesis, and the TFHE library is one of the famous libraries for fully-homomorphic encryption. And what seems to be happening is that they have a pipeline where you give in your C++ code and it goes through different transformations, and then it ends up in a format that's suitable for the TFHE library, and the TFHE library is the one doing the heavy lifting. There is an explanation of how this works on a high level, and it's here in the design paragraph. What happens is that our C++ code is converted into an XLS IR. Then at the second stage it's being optimized, and then it's being converted to, I would assume, some kind of a circuit where it only uses fundamental Boolean operations. And then one of the interesting parts is that stage 4, this is being transformed into a special type of FHE C++, which is C++ that can work on encrypted input. And then in stage 5 we write a simple program where we run this code and see how it works. Now if we scroll up a bit and look at how this library can be installed, we see two options. Option A is to install it on your machine manually by installing the dependencies and, I would assume, compiling locally. And option B is using Docker, and I've decided to use Docker. It seems like it's easier and much less things can go wrong. What they say is that we need to check out the code first, and then we need to execute this command, which will generate an image for us with the library compiled inside. And this took a long time on my machine, so I'm not going to show it on video. I've already done it, and the result is this image here, and it contains the compiled library. Another interesting point I wanted to make is that I'm using an M1 Mac with an ARM CPU. I'm not using an Intel CPU, and I had to make some changes to the build process for it to work. The first thing I needed to do is, if we look at the Docker file, we see that we're downloading an Intel Bazel binary, which obviously will not work. Instead, we need to download the ARM64 version of this binary, and that's why I've changed the Docker file accordingly. The other change I had to make, which was more interesting to me, was that the TFHE library by default uses x86 assembly for FFT, at least the way I understand it, and I haven't looked at the code in great detail, but that's what I saw. And obviously x86 assembly will not work on M1 Mac. That's why I had to turn off essentially these optimizations for FFT and instead enable a portable version of FFT written in C, if I'm not mistaken. This is interesting on another level because I've seen FFT being used mostly in signal processing, for example audio or video processing, also in radio networks, and I haven't seen it in this context. And I just had a brief look, and it seems that they're using it to multiply big numbers, and that's something I'm going to investigate maybe in a future video, because I think that's an interesting concept which I haven't gone into too much detail. Like I said, I am not a cryptographer. Now we can run this command to make sure that it actually works. I'm going to copy and run this image, and now we can run one of the demos. I think a good one would be the one that's summing two numbers, as we already discussed it. I'm just gonna copy this command and run it inside the container. What I need to change though is I need to make sure that I'm not using Bazel, I'm just using Baselisk. I'm not exactly sure why I need to do that. Maybe I'll investigate later, but I guess it's not terribly important for examining the library. Let's run it. What it's currently doing is it's making sure it doesn't compile things again. They've already been compiled, and what it's doing essentially is summing these two numbers and saying that this is the expected result, and it's kind of simulating a quant server architecture. It's encrypting these numbers on the client side with a private key only known to the client. Then it's sending over to the server. The server is executing the computation on the encrypted numbers, and then it's returning the encrypted result. And here the client can decrypt the result, and the result is as expected. And what's important is that the result is encrypted with the same private key that was used to encrypt the inputs. So this was kind of a smoke test, and it shows us that the library is working. Another thing I want to do before moving on to our mail spam example is to make our lives easier by copying the compiled library out of the container to the host and then mounting with a Docker volume. And I want to do that because I don't want to recompile everything all the time, and it will be just easier for us. So in order to do that, I'm going to start the container again. Actually, before doing that, I want to create a directory on the host where I'm going to copy the compiled library, so I'm going to call it compiled. Run the container with this directory mounted, so I'm going to do something like that. I'm going to mount it at /compiled just to copy there, and I'm going to copy the whole directory, so I'm going to copy user source fhe to /compiled. Then I'm going to remove the fhe directory from the container, so I'm going to do remove user source fhe. I'm going to just put these flags, and then in another terminal I just want to commit this container so that it doesn't contain the compiled library. So I'm going to do docker commit and then call it with tag it with volume like so. Then I'm going to exit, and then I'm going to start it by first of all using the new image, the with volume one, and then I'm going to mount the fhe directory from the host to user source fhe, so that everything is using the same paths inside the container. Make sure everything looks good, and then just a quick smoke test, summing the numbers as before. As you can see, everything's good. An interesting application is email spam detection. I came across this example on Vitalik Buterin's page, and it goes like this. Suppose you want to check if an email is spam, and you want to use a third-party service for that. The problem with using a third-party service obviously is that you don't want to share your email, but yet you want to check if it's spam. So that's where FHE can be really useful, in the sense that you can encrypt your email, send it encrypted to the server, and then it can run its algorithm on the encrypted email and tell you whether this is spam or not. This is explained here in this diagram. The client encrypts the email with its own private key that's not known to the server, sends it to the server. It can then run its algorithm to detect whether this email is spam, and then return the result back to the client. This is something I want to implement with the FHE library, because it seems like it's simple enough and seems like a probable real-world application. Essentially, to simplify things, I'm thinking of just looking for a specific string in an email, for example some bad URL that is classified as spam, and if the email contains this string, then we're going to report it as spam. Obviously, this is just a simple problem of looking up a string in another string. There are library functions for that, For example, standard string in C++ can do that, and also the string function in the C library, but I'm not exactly sure if these functions will work. We will try it. And the reason I don't think they will work is that there are some limitations to the library. If we go to this paragraph in the README file, it's saying that there are three major limitations. The first one is that variable length arrays are not supported, which I think directly excludes standard string, and also I think excludes row char pointers, but we're going to try it still. And also a big limitation is that there are no early returns from loops. I think this will exclude lots of library code too, and limit what we can do. There is a workaround, obviously, to have a break statement inside the loop, and I think we're going to have to use that. And also floating point numbers are not supported, but I think this doesn't concern us. So let's go and let's try to implement mail spam detection. So the first thing I'm going to do is I'm just going to copy the simple sum example and change it so that it does spam detection. Spam. And now we have this directory, and there are a number of files here. This one I think is essentially not using encryption, it's just making sure that the library internals work correctly. I'm not going to bother with it, I'm going to remove it. This one is just a gtest unit test, which I'm not going to also bother with. I'm going to remove it. And I'm going to obviously change the name to mail spam. Mail spam. Okay. And I'm going to need to change the build file, so I'm going to change all currencies to everywhere. Okay, and since I removed two of the binaries, I'm going to have to remove them from the build file. This one, I think, actually this one, I'm not going to use it. And the test also, I'm going to remove it. So let's first think about the interface of mail spam detection. Essentially I want to return a boolean saying whether the email is spam or not, and for now I'm not going to accept any parameters. I'm going to change the header, and I'm going to implement this function here in the CC file, and for now I'm going to just return true. What's important to mention is that the function that's going to be used for fully homomorphic encryption needs to be tagged in a way via this pragma top, which I think means the top level function. Now let's have a look at the test bench file, which is the main function of our program. I'm going to again change simple sum to mail spam everywhere, and let's look at the code. First of all, we generate a key set, which I think this is just the private key of the client, and to generate a random key, we need a seed, and that's where we generate this key, and then essentially we're just summing the numbers. But now I'm going to change all of this. First, there are no integer inputs. I'm going to remove this. I'm also going to remove this. Actually, I'm going to comment this because I think I'm going to use it. This is something I don't want to print. And here we're going to call the mail spam function. We'll say mail spam detection here. And the way it works is that basically the first parameter here, first of all, this is a function that has been generated. It's not our function. and the first parameter it gets is going to be the result. In our case, this is going to be a boolean of whether this is email spam or not. And since we don't have any parameters yet in our email spam function, I'm just going to remove these two parameters for now. I'm just going to pass the key, and I'm just going to leave these walk statements, and we're going to expect that this function always returns true. So when we run this program, we should see that the result is always true. Okay, so let's try and run our example inside the container. Needs to compile it this time. And I just hope I haven't made any mistake. Okay, it seems to be working. And now we need to add a parameter for the incoming email. So I think let's first try the simplest thing. Let's just try to include and then use a const reference, something like that. Let's just first see if this is going to work. Yeah, so there's no such header string. This was a long shot. I doubt that we can use the standard library when writing FHE programs, so we're not going to do that. Let's try something simple. Let's instead pass a const char to represent the string. Yeah, change this, and let's just try compile again. So what it's now saying is that pointers are unsupported, which is fair enough. I think there's no way to pass in a dynamic array like that. As the limitations were mentioning, we cannot have variable length arrays. So we need to try another approach. What we can do is maybe we can define max mail size to be equal to, let's say, 64 bytes in unsigned, and then let's pass in a built-in array of that size, something like that. Now the compiler will know what the size of the array is, and we should be good. Let's just try. Actually, we cannot do it because now we need to pass in this parameter. So let's pass it. Let's create. Actually, first thing we need to do is to include the file mailspam.h, because that's where the constant is. We want to read the email from the command line on the client side, and in order to do that, on line 50 we create a standard string and initialize it with the first argument of the program. And then on the next line, what's interesting is that we need to resize it so that it's exactly max mail size number of bytes. And the reason for that is, if you remember, we had to use a built-in array with a fixed size of exactly max mail size because we couldn't use dynamic arrays. And that's why here we need to make sure that the parameter that we're passing in is exactly max mail size. And then on line 53, what we're doing is again on the client side, we're encrypting the email with the client's private key. And we're getting the encrypted email, we call it mail ciphertext. And this is the parameter that we're going to send over to the server. And in order to do that, we need to add it as a parameter to the ismail spam call, mail ciphertext here. And now the call to ismail spam has three parameters. The first is the result, which is going to be essentially a boolean of whether this is spam or not, the encrypted email, and then this is a special key that is required by the server, which comes from generating the client's private key, but this is not the client's private key, so this key cannot be used to decrypt the data. I'm not fully sure how this key works. I'll investigate later, maybe in a separate video, talk about it. But what I've seen in the documentation is that the server cannot use this key to decrypt the email, but it's definitely using it for something, which I need to look into in more detail. And one more thing to mention here is that the cipher result, which is essentially the boolean, is of type FHE int, and this is just a type def to an FHE value of int, and I tried to type def it to FHE value of boolean, but it wouldn't let me do it. It's forbidden. So essentially what's going to happen is we're going to convert a boolean to an integer for the result of mouse spam detection. And then the last part is we're kind of simulating that the quant is getting the encrypted result and it's using its private key to decrypt it and print whether this is spam or not, and this happens on 164. So let's try run this program now. You can see here that I'm passing in an argument, and this is the email we're going to check for spam. And if I run it, okay, we see it's working, but we need to write the actual mouse spam detection function. What this function actually does is check whether a certain URL is part of the email, and it does so in a really simple way. It starts at the first character of the email and checks whether the URL starts at that character, and then goes character by character. And we can see that it's doing that here. There is a for loop which is iterating from 0 to max mail size, and then it checks whether we've reached the end by checking for the no termination. And by the way, I tried to short circuit these two expressions in a single if statement, but the compiler didn't allow me to do it, so I just split the two if statements. The first one checking whether we are at the end, and then if we're not at the end, we're calling a helper function which checks whether the URL starts at position I in the email, and if that's the case, we can break and set the boolean to true and report that this email is spam. One more thing to mention here is that we need to mark loops with this pragma to unroll them. This compiler requires it. Let's look at the contain spam function now. As I was mentioning, it just tries to find a specific URL in the email starting from offset. And what we do here first is we specify the spam size to be a static const expr value. I couldn't use size of, I couldn't use static arrays with automatically deduced size, so that's why I had to manually calculate how big the array is, and in this case it's eval.url, so it's like 8 bytes and 1 byte for the no terminator, and then we just iterate over the spam URL until we're at the end, and if we're not at the end we move on and we check whether we've reached the end of the email itself, and if not, then we check whether the characters at the specified positions are different, and if that's the case we say that this is not spam because the URL is not part of the email at that offset at least, and actually that's it. This is a very naive implementation. It has lots of drawbacks, but it works for this example, and I encountered lots of limitations. I guess there is a better way to do it, and I'm going to spend more time with the library and hopefully I can make it better. Let's first pass in a mail that is not spam. Let's say the contents are safe email, and then run it. And here we can see it's working because this was a non-spam email and the result is 0, which means that this is not spam. So let's now try passing a spam email. I'm going to call it click and then pass in the evil URL. And now let's see if this is detected as spam. And we can see now the result is 1, which means that this email is detected as spam, and that's the correct behavior, so it seems it's working correctly. One more thing to mention here is that it took a lot of time to detect spam on my machine, and this is just a MacBook M1 laptop. It took something like 2 or 3 minutes to detect And these are really small emails and really small URLs. It seems there is a way to go to make this more practical, but it's still really exciting even as it is. So there we have it, mail spam detection with fully homomorphic encryption in C++. I have a few more ideas for videos that further explore this library. For example, I was thinking I can have an actual client-server architecture where the server uses HTTP and maybe I post a JSON to it and then it responds back with a JSON. This is something I can do in a separate video. And the other one is maybe if there is a way to make the spam URL configured in a way, in the sense maybe I pass it from the outside and somehow I compile it in the binary itself, and maybe pass in multiple URLs so I can check them one at a time. If you have any other ideas to experiment with this library, please let me know and I'll try to implement and make a video. I think fully homomorphic encryption is really exciting and I'm definitely spending more time with it. Thanks for watching.